All right, welcome back. So we're looking at past questions today. So as usual, you can get your questions from the description, okay, below, and you can go ahead to try solve them on your own and then come back. These are questions from exams like the WAEC and the JAMB exams. So the first question says, the mechanism of heat transfer from one point to another through the vibration of the molecules of the medium is, okay. So we remember from the class when we talked about conduction, convection, radiation. Okay, so our options have all that, all three of them, and then has diffusion. But talking about vibration of molecules, okay, we know that radiation is being transferred without any medium, so it doesn't even require vibration. We know conduction, convection is, we know convection has to do with bulk movement of matter. You don't have heat transfer by vibration of particles. Okay, so that only happens in conduction. So our answer for number one is conduction. Which of the following concepts is a method of heat transfer that does not require a material medium? I just talked about it now. So of course we have the same options with diffusion included, but the answer to this is radiation. Number three, which of the following is not an application of expansion in metals? Okay, one, we have bimetallic strip thermometer. 2, we have temperature control in an electric iron. 3, we have compensated balance wheel of watch. D, we have sagging of telegraph wire. There is application and there is effect. All right. Okay, so let's look from A. So bimetallic strip thermometer, is that an application or effect? Okay, that is an application of expansion in metals. Okay, so and the question is, which of the following is not? So we skip that. Temperature control in electric iron. Of course, temperature control in an electric iron is done by the bimetallic strip. So we already know that is an application. So we skip it. Okay, we have C, compensated balance wheel of watch. That's also an application. Okay, because that has to also do with the bimetallic strip being used to avoid some effect of, the expansion in metals. D, sagging of telegraph wires. Is that an application of expansion in metals? No, it's not. Okay, because sagging of telegraph wire is just done, okay, to prevent wires from breaking up when temperature changes and they have to expand or contract. Okay, so but that's not a direct application of expansion in metals. It's a prevention technique. Okay, that doesn't involve the application of this. It's just a prevention technique that helps to avoid the negative effect of expansion in metals, but it's not a direct application. Let's move on. Number 4, which of the following cannot be used as a measure of the degree of expansion in solids? We have linear expansivity, cubic expansivity, area expansivity, and apparent expansivity. Obviously the answer should be D. Okay, of course we talked about linear, cubic, and area expansivity. So apparent expansivity cannot be used to measure the degree of expansion in solids. Right. Number 5, the thermal expansion of solids is an advantage in A, balance wheel of watch, B, construction of steel rail lines, C, construction of large steel bridges, D, fitting of tires on wheels. Okay, so our answer here should be A. Okay, so let's look at this from the last option up. We have fitting of tires on wheels. Thermal expansion is not an advantage there. We have construction of large steel bridges. Thermal expansion here is not an advantage. If you have large steel bridges expanding after you've built them, it's actually very dangerous because it's even actually going to lead to the destruction of the bridge. Construction of steel rail lines, the same thing. For the balance wheel of a watch, of course, it helps us in the watch to get accurate timing. So you see that application there is an advantage. So our answer will be A. So we'll move on to number 6. The linear and cubic expansivity of a material are related by the equation gamma equal to A, gamma equal to 3 alpha, gamma equal to 2 alpha, gamma equal to 1 over 3 alpha. Of course, this D self is out of it completely. Okay, so we know that gamma is the cubic expansivity, and we know that alpha is the linear expansivity. So what do we think it is? Of course, cubic expansivity is 3 times the linear expansivity. So our answer is B. Now we'll move on to number 7. metal of 40 centimeter cube is heated from 30 degrees Celsius to 90 degrees Celsius. The increase in volume is, okay, we're asked to find the increase in volume. So of course we have the two temperatures which is heated through, T1, T2, and we have the initial volume. So we're asked to find the increase in volume, which is V2. Okay, so what we do is, let's bring out our parameters first. We have V1 to be 40 centimeter cube. We have T1 to be 30 degrees Celsius. We have T2 to be 90 degrees Celsius. We have alpha to be 2 times 10 raised to power minus 5 per Kelvin. Okay, so what do? We bring in our formula for cubic expansivity, which is gamma equal to change in volume over initial volume times change in temperature. If we put in our parameters here, of course, this is equal to 3 alpha. Now, the reason why we're using 3 alpha here is because we don't have this guy. We don't have the cubic expansivity. So what we're given is the linear expansivity. So we have to use the linear expansivity to solve this question. But we know that cubic expansivity is 3 times the linear expansivity. So we're replacing this with this. Okay, so and then make change in V a subject of formula, and we're going to have 3 alpha times V1 times change in temperature, because we're actually looking for V2, and this is only where we can get V2 from. So if we put in our values, of course, we have 3 times 2 times 10 raised to minus 5 per Kelvin. This is alpha times 40 centimeter cube, okay, which is V1. Then change in temperature, 90 minus 30. So that will give us 0.144 cm cube, which happens to be the change in V. Okay, I need you to note that we're not asked to find V2. We're asked to find the change in volume, but was said as the increase in volume. We now move on to number 8. The diameter of a brass ring at 30 degrees is 50 centimeters. To what temperature must the ring be heated to increase its diameter to 50.29? Okay, so we have a brass ring. We know the diameter of the ring at 30 degrees. They're asking what will be the temperature if this ring finally gets to 50.29. What temperature can move it through this increase in diameter? So of course, we have linear expansivity of brass given to us down here. Okay, so let's bring out our parameters. We have L1, T1, L2, alpha, and we're finding T2. Okay, so basically what we need to do is to use the formula for linear expansivity, okay, which is alpha equal to change in length over unit length times change in temperature, or per degree rise in temperature. And so if we bring in our parameters here, we have 50.29 minus 50, that's the change in length. The initial length is 50 centimeters, and then we have change in temperature. Okay, so of course this cm will take out this cm. All right, now our unit here is in Kelvin, and we did not change this to Kelvin. Okay, and that's because whether you're in the Kelvin scale or you're in the Celsius scale, okay, once you're subtracting to the two different temperatures, they're going to give you the same value. Okay, so we have T2 minus 30 here. Okay, so let's move on. So if we simplify this, we have 0.29 divided by 50. Okay, so we're going to look for a way to make T2 the subject of formula so that we can find it. So we have T2 minus 30 as subject of formula. So we finally pulled it out from down here, and then we have that to be 0.29 all over 50 times this, which is our alpha, linear expansivity. Okay, so making T2 the subject of formula now, we move 30 over to this side. Okay, so if we simplify that, we have 335.3 as our answer. Okay, so 335.3 degrees Celsius. So number 9, the length of an iron bar is 100 centimeters at 20 degrees Celsius. At what temperature will its length increase by 0.01%? Okay, so we're looking at a 0.01% increase. Okay, so let's bring out our parameters. We have L1 to be 100 cm, T1 20 degrees Celsius, change in length 0.01%, alpha we have 1.2 times 10 raised to the power minus 5, okay, per Kelvin, and we have T2 to be unknown. So what we now do, we need to find what 0.01% increase means. Okay, so 0.01% increase is 0.01 times 100 cm, and that will give us 0.01 centimeters. So it means we're looking to increase the length of the iron bar by 0.01 centimeter. Okay, so we move on to adding 0.01 centimeter to the previous length to get the next length, which is L2, and that will give us 100.01 centimeter. So the question is to know what temperature this will happen. So we put this into our equation, which is the equation for finding linear expansivity. So if we put this in, we have change in length to be 0.01 cm. We have our L1 to be 100. Of course, remember we got 0.01 cm as change of length from the percentage increase we solved. This is not L2. This is the increase, the increment. So you add it to what you have and you get L2. Okay, so we find a way to make T2 subject of formula. If we do so, we're going to have 0.01 divided by 100 times the linear expansivity. Then we add all that to 20 degrees Celsius, and then we're going to get our answer to be 28.33 degrees Celsius. So these are the steps you can follow to solve that problem. So number 10, we have a glass bottle of initial volume 2 times 10 raised to the power 4. We heat it from 20 to 50 degrees Celsius. If the linear expansivity is 9 times 10 raised to the power minus 6, what is the volume of the bottle at 50 degrees Celsius? We have our V1, obviously, we have our T1 and T2, we have alpha, linear expansivity. We have to find V2. Okay, so we can easily equate the cubic expansivity to linear expansivity like we did before. Okay, so since we're looking for V2, obviously we're looking for the cubic expansivity from V1. So if we put in our values into this equation, we'll have this. So we're going to find a way to make V2 the subject of formula, so we can take this over to this side for them to multiply out themselves. We can then move on. So once we've simplified this denominator, we can then simplify further to get V2 as this. Okay, so if we type this into a calculator, we're going to have V2 as 20016.2 centimeters cube. So number 11, we have the mass of an empty density bottle is 30 grams. When filled with a liquid, the mass of the bottle and the liquid is 40 grams. On heating the filled bottle through 40 degrees Celsius, the mass reduces to 38 grams. Calculate the apparent cubic expansivity of the liquid. Okay, so let's bring out our parameters. All right, we have mass of the empty bottle, we have mass of bottle plus liquid, we have mass of heated bottle plus liquid. Okay, and we know from our class that apparent expansivity is mass of liquid displaced, all of our mass of liquid in container times change in temperature. So we just bring in our values here. Mass of liquid displaced is obviously 40 grams minus 38 grams. Okay, because this is mass of bottle plus liquid for the 40 grams and mass of heated bottle plus liquid for the 38 grams. So it means for this to be the case, mass was lost. So to get that mass of liquid displaced, we have to subtract 38 from 40 and divide by the mass of liquid in container, which is 8 grams. And this 8 grams is coming from mass of empty bottle, which is 30 grams, subtracted from the mass of heated bottle plus liquid. So if you have our bottle to be 30 grams, then if you subtract that from 38, you'll be left with the liquid, which is 8 grams times the change in temperature. So if we simplify this, we have 2 grams divided by 8 times 40 degrees Celsius, which gives us 6.25 times 10 raised to the power minus 3 per Kelvin. Okay, so let's move on to number 12, which happens to be the last question. A wire of length 100 meters at 30 degrees has linear expansivity of 2 times 10 raised to the power minus 5 per Kelvin. Calculate the length of the wire at the temperature minus 10 degrees Celsius. Obviously, we have our parameters here on the screen. We're looking for L2. We have L1, T1, T2, and we have alpha. So we use linear expansivity formula to solve this. Okay, if we bring in the parameters, we have L2 minus 100 meters divided by 100 meters times minus 10 minus 30, and that gives us 2 times 10 raised to the power minus 5 per Kelvin. Now, you can see that our temperature is given in degrees Celsius. Okay, and we didn't change it to Kelvin here, and most people are going to get confused at that. But the truth is, no matter the scale you're using, whether it's the Celsius scale or the Kelvin, okay, the difference between both temperatures will give you the same value. If we do this in this scale of degrees Celsius, we're going to have -10, -30, which will give us -40 degrees Celsius. So let's do this in Kelvin. So in Kelvin, okay, -10 here will be 263.15. Okay, while 30 degrees Celsius, okay, will give us 303.15. All right, so -10 is this. So if we subtract 303.15 from 263.15, because that's what we did here, you will see that we're going to get our answer as -40. All right, which is what we have here for the Celsius scale. So the point is, once it's a difference happening, no matter the scale you're using, the difference is going to give you the same answer. Okay, so moving on, we make L2 the subject of formula, and then we have our answer to be 99.92 meters